the next lecture in our energy unit is on atoms and isotopes. Now, you might notice that we're moving from heat and thermal energy to a new type of energy, nuclear energy. But before we learn about nuclear energy, we do need to understand a bit about atoms and isotopes. So first we'll go through the history of atoms. And it was actually, the history of atoms goes back to the ancient Greeks. There was a philosopher named Democritus who asserted that all material things are composed of extremely small, irreducible particles, and he called them atoms. Now, his theory was rejected, but in the early 19th century, John Dalton, he resurrected this atomic theory of matter, and the idea of materials and things being built of these small indivisible particles, what they thought were indivisible at the time, atoms. And over the next 100 years or so, scientists continue to refine their understanding of the atom. Originally, the atom was an indivisible piece of matter, but then we learned that there are atomic components that make up the atom, and then there's other things that can make up those things. So let's read on here. It says, in the 19th century, while investigating the nature of radioactivity, Frederick Soddy discovered between 40 and 50 previously unknown elements with the same chemical properties as known elements, but with different radioactive properties. So what Frederick Soddy figured was there were these elements that were just like other elements on the periodic table, but they were more radioactive, or they had some were more radioactive, others were not. Essentially, what he found were isotopes. So they were elements and that had different neutrons, or different amounts of neutrons in their nucleus, and because of those extra, or because of the deficit of neutrons, they became radioactive. So these now, not all isotopes are radioactive, but the idea of different isotopes of elements earned Frederick Soddy the Nobel Prize for Chemistry in 1921, and it helped make further our understanding of how elements react and act with each other, and you see common isotopic versions of elements listed on some periodic tables now. So Soddy coined this term, isotope, to describe these different forms of the same element. Isotopes are atoms of a single element that have the same number of protons, but a different number of neutrons. So carbon-12, that's the most common form of carbon. It has 6 protons and 6 neutrons. But there are other types of carbon. One you might have heard of is carbon-14. It has 6 protons and 8 neutrons. Now you might notice where that number, that 12 and that 14 number, come from. It's the atomic mass of the atom, either the regular form, the normal form, or the most abundant isotopic form, and the rarer type of isotope that you would find. 8 plus 6 is 14, so carbon-14, its mass comes from that. 6 plus 6 is 12, so that's where we get the 12 from carbon-12. And what you're seeing down here is the an indication of how to represent an isotope. We write the symbol of the element, C. We write its mass, 12, and we write the number of protons, 6, so that we know that we can find out how many additional neutrons it has by subtracting those two numbers. Most samples of elements consist of a number of different isotopes. Some occur naturally, and some of them are produced in laboratories. So the most common isotope of hydrogen, it's known as protium. and it has a nucleus consisting of one proton. But there are two other isotopes of hydrogen, and these are important isotopes, especially for nuclear science. We have deuterium and tritium. So deuterium has one additional neutron that makes it H2 in terms of the isotope of hydrogen, and tritium has two additional neutrons. So copy this down here, and you can copy down the common isotopes of hydrogen as well, because these names, hydrogen, deuterium, and tritium, you might see them in some textbook questions or questions on tests, and it's assumed that you know what they are. You also can see their isotropic formula, H11 for our typical hydrogen isotope, or protium isotope, 21H for deuterium, and 31H for tritium. Now, I did kind of say that most isotopes are radioactive. You can't exactly say that. There are a lot of radioactive isotopes. They are also known as radioisotopes. They radiate energy, and over time they could lose particles as well. So the radiation they give out is an electromagnetic radiation, and it occurs regularly throughout the I guess I shouldn't say regularly, but for a certain mass made up of radioactive isotopes or radioisotopes, a certain number of them will give off a particle and turn into a more neutral isotope. When that happens, a certain amount of radiation is given off, but we don't know exactly when the radioisotope will give off its radiation. So this is where we don't know exactly how long a radioactive material will be radioactive, but we do have a good understanding with what's called half-life, and we'll get into that a bit later. So the radiation that radioisotopes can give off, it may be harmful, but we can control it, and there are some radioisotopes that are beneficial. We found uses for them. So you can copy these definitions down. A radioisotope is an unstable isotope. Radiation is a form of energy released when a radioisotope spontaneously changes its nuclear structure, and it is dangerous, but it can be useful. So just to kind of go back to the explanation again, let's say we had a material that was made up of 100 radioisotopes, and during the let's say we look at that material for a full day. Well, maybe half of those radioisotopes have now given off their radiation. We have 50 radioisotopes left. The next day, you might think half of those would go, but maybe only 10 of them go, not a full half. So that's why it's hard to say how much how long something will be radioactive for, but half-life gives us a good understanding of the average amount of time it would take for that material to reduce to half of what it originally was. One use of radioisotopes is through nuclear imaging. This is when a small dose of radioisotopes are injected or ingested by a patient, and then we can observe the radiation that's given off. And in a case where we're trying to look at how things are building up inside of the body, we can now see the radiation of where those the injected or ingested material is pooling. One of the advantages of nuclear imaging over traditional X-rays is that it provides a detailed account of both hard and soft tissues, whereas the X-rays can only really be used to detect bone fractures, so that's hard tissue. So we can use radioisotopes and nuclear imaging to look at some softer tissues and kind of image those. So you can copy this slide down for nuclear imaging, one use of radioisotopes. One of the earliest medical applications of radioisotopes was in the 50s. Iodine 131 was used to diagnose and treat hyperthyroidism. Now, when we write down something like iodine 131, what that basically means is that iodine is the element, 131 is the mass of that isotope of iodine. So iodine 131 was used to treat hyperthyroidism. The thyroid gland is an important organ of the endocrine system. It's located in front of the neck, just below the voice box. It produces glands, or the gland produces hormones, which control the way every cell in the body uses energy. It was found that you could treat this using a radioisotope. Radionuclide therapy, RNT, is a rapidly growing medical field in which the properties of certain radioactive substances are used to treat various ailments. In cancer treatments, the fundamental idea behind RNT is to bombard rapidly dividing harmful cells with radiation. These cells tend to absorb the radiation, which prevents them from further dividing. So here's something else you can write down for a use of radioisotopes. Cancer cells are bombarded with radiation. The cells that absorb the radiation then are unable to divide. In agriculture, radioisotopes are used as well. Gamma radiation is used to kill insects stored in wheat and flour. Also, selective breeding of irradiated seeds has produced beneficial mutations. In this manner, we have created disease-resistant and high-yield crops. But this raises some questions about safety. So is it safe to irradiate our food? One scientific study identified chromosomal changes in irradiated wheat. Other studies have shown that radiation causes chemical changes which appear to affect the cell structure of the food. The radiation that kills bacteria by preventing cell division may result in other changes in the food. So the question is, are these changes worth worrying about? Radioactive tracers have many industrial uses as well. They're used to study the effects on plants of growth hormones, pesticides, fertilizers. They're used by manufacturers of soaps and detergents to test the effectiveness of products in removing dirt and clothes. In this process, radioactive tracers are added to the dirt, and then the clothes are washed. The proportion of dirt removed during washing is measured indirectly with the radioactivity. Tracers can also be used to find leaks in underground oil pipelines and to measure the erosion of piston rings in a car engine. So for testing a soap, you could qualitatively measure the amount of dirt that's been cleaned off of it, or you can quantitatively measure the amount of radiation that the clothes no longer have after washing. And that's the idea behind radioactive tracers. And the last slide we'll look at here, it says, tiny nuclear reactors are used as energy sources in remote places such as polar weather stations and in scientific instruments left on the moon. Cardiac pacemakers with plutonium-238 power sources last as long as 40 years. Priceless art treasures such as oil paintings, wood sculptures, and tapestries can be preserved from decay by exposure to gamma radiation. And those are just a few of the many uses of radiation.